Welcome back. We're going to talk about the texture of metamorphic rocks and how they change and what they change into and what the appearance of these rocks would be. We're going to see that the pressures and the temperature changes that those rocks are enduring are causing stress to that rock. They're stressed out. And as a way to alleviate that stress, often they can change the shapes of the way that the crystals are aligned inside the rock. If the crystals can line up in such a way, it alleviates the stress. So imagine that you have a big pile of crayons on the floor, and you are going to pick up a big wad of crayons at a time. So you just reach out your hand and you grab a bunch of crayons, and then you pull your hand close, and the crayons will align themselves, stack up really, so that they will all be lined up in the same direction that your hand is. That's really what's happening with these crystals. So the textures that you see, the resulting shapes, and the way the rocks look at the end, a lot of times is to alleviate that stress. So you have some kind of a pressure or temperature difference that can be alleviated by realignment or recrystallization, then that rock will, and then the resulting shape changes based upon that. I've mentioned before that you can have different stresses on rocks and that have different effects. So if you have low-grade changes, so if you were to put a rock under pressure and temperature, that would change that rock slightly in order to alleviate the stress, then you could simply compact that rock and make the same amount of matter in a smaller space. So you could basically just increase the density of that rock. If you put some serious stress on it, you could actually recrystallize the minerals inside that rock, or change the size of those minerals within that rock so that you could compact the minerals inside the rock. So there's basically a breaking of bonds and a forming of new bonds in that same material, so that the rock that you have at the end has a different composition than the rock you had at the beginning. So one of the processes that a rock can undergo in metamorphosis is foliation. So foliation is the idea of leaves. And so if you can take these minerals that have some kind of a 3D shape and then under high stress basically line them up. So they're trying to get out of the way, and as they do, they line themselves or orient themselves in one direction. Many of these metamorphic rocks will be striped. You can look at them and see that the crystals inside are all lining up in one direction. So it looks like that there are stripes inside the rock. These stripes are even more apparent if you have different colors of minerals inside your rock. So if you were to have something as obvious as black minerals in a white and white minerals together, a lot of times you'll have a lining up of this in such a way that all the light minerals kind of pack in one place, and then in a different layer you'll have the dark minerals. It's usually because they're of different size, and as they're trying to get out of each other's way, they tend to line themselves up. You can also have just basic ideas. If you were to have a long crystal, say a chain of silica or something, they could all line up in one direction, like a flat micas inside a piece of granite that's turning into gneiss. Also, if you had a rock that was made up of different particles, those, say, smaller stones inside a sedimentary rock could all align themselves up to where they're all lining in the same direction. You're not going to have foliated rocks all the time, so you're not going to have these stripage. It really depends upon what are the minerals that make up the parent rock, and do they stabilize by shifting themselves. So if you have a non-foliated rock, you don't have this deformation of the minerals. There's no real benefit to lining minerals up because it wouldn't reduce the space or alleviate the stress. So some rocks will be obviously striped or foliated when it's metamorphosed, and others not. So let's look at a few of these examples. The one I learned first was the idea that that shale, which is a sedimentary rock made basically of very fine particles of mud or silt, can be changed into slate. And slate is a very hard, flat rock that splits in sheets, and you use them on tiles, roofing tiles of old buildings. So everything lines up in such a way that all of them are configured in flat cleavage slabs that you could break into tiles. If you were to have that same material and you have different pressure points, you can actually make all of those tiny flakes bend and curve, undulate back and forth, and then you would have phyllite. If you were to have mudstone or shale also, and depending upon the stresses, you could get some foliation, slight foliation, where you would have kind of a dark areas, white areas, dark areas, and then under very high pressure, you could actually stripe those out, and so that all of the white minerals would kind of align and all of the dark minerals inside would align. So the hornblende inside the albite, for instance, I think would be this example, to where you'd end up with a zebra-looking rock. In the case of limestone is a sedimentary rock. They don't have any stripes in them, so there's no foliations, but you do have, if you've ever seen a piece of marble, you do have kind of colorations in the marble, kind of a grain. It looks like a grain. So you have these kind of wavy lines inside the marble. Quartz can do the same thing. If you have a sandstone, which essentially is made out of silica, which is quartz, it's not going to stripe or anything like that, but you can end up with a quartzite rather than a quartz. So this should be a review of what we just saw. Slate is cleaved, has a cleavage line in such a way that you could actually break them into roofing tiles. So that's shale that's been metamorphically changed. Phyllite is a little bit bigger grained and different pressure points, so that you end up with waving, kind of a grain pattern in it. Schist is shale that is not necessarily striped, more of a speckled kind of a metamorphic rock where everything is kind of getting out, so that would be just a slight metamorphic pressures. Gneiss would be much more, so that's banded. You end up with a granite that can be turned into stripes, and that's gneiss. You can see too that not just the texture changes in metamorphic, but also the hardness and the resistance to breakage. So for instance, in the case of quartzite at the bottom here, if those quartz pieces are actually fused together, then that rock becomes ridiculously hard. And a lot of these granites will be changed into quartzite deep underground because of just the weight of the mountains that are pushing down on the bottom of them. Marble, if you've ever seen a statue that's made out of marble, a statue is easy to carve because it's very, very fine crystals. And so they catch the light beautiful, they can be polished beautifully, and these crystals were from the tiny little sediments that formed the limestone that marble was based on. So to review, if the parent rock is not under equilibrium, meaning it can move, if it moves, it can reduce the stress that it's under, then it will move. Either the grains will move, or it will shift in such a way, or they will recrystallize. So you can get changes not just in the texture, you can actually get changes in the configuration, the way the mineral actually looks, even in its chemical composition, depending on what those stresses happen to be.